So good morning. Thank you to be here to attend this first presentation. I will talk about a new development process deployed at Valeo engine management system to develop AUTOSAR software components. So first, I will describe the context. I think it's very important. I think the first issue with automatic generation of code is to switch from previous process to automatic generation process. It's to take the decision. We got a very robust and validated process with hand-coded processes. And the first issue was to decide to go to automatic generation of code for production code, for sure. Then I will describe the development process by itself. And as a conclusion, I will talk about benefits, issues, and improvements that we still have to do. So development context. So first, Valeo engine management system. We developed full engine management system, but also components and also software components, previously as standard software and now as AUTOSAR components. So today we'll for sure focus on software activities development, including control law development and implementation. So the first element was a main improvement done on our functional architecture system. And due to functional requirements such as hybridation, downsizing, and so on, we had many architectural, functional, and also performance improvement to do on our system. We are used to work with model-based since many years, like everybody for sure. And in this context, we also introduced latest model-based processes. I mean, we introduced systematic simulation. We used to do simulation like everybody, but during this improvement, systematic simulation were done on all our systems. And rapid prototyping was used as validation of new functions. Okay. The second point is the AUTOSAR context. We had to develop those new functionality as applicative software component, just because it was a customer requirement. And due to this constraints, it was very difficult to us to reuse existing software, so we had to start from scratch. And to integrate those new software components in an existing software, so mixing old architecture with AUTOSAR architecture. The last constraint that we had was an organizational request who wanted to be able to switch from AUTOSAR architecture to standard architecture. And due to all those constraints, we choose to start with automatic generation of code at this time. Okay. So the development process by itself, I will first talk about functional design. Models that are developed are used during simulation, during co-simulation, and are then used with rapid prototyping to be validated on test benches. And Functional requirements are introduced in the models and in the test environment, OS and stimuli. And functional requirements are expressed as signal builder behaviors, and they are delivered as a standard element of specification. So with this process, algorithms are robust due to validation, and all what is requested by software teams are delivered at the output of this step. I mean, we've got the model okay for the automatic generation of code, but we have also simulation and stimuli sets that we will use during all the process to test non-regression of the implementation. So for the rapid prototyping, one important point is that we use rapid prototyping platform based on the final microcontroller. It embeds more flash and more RAMs, but the CPU is the same and the hardware definition is the same. So we've got something very representative with the final ECU. And as the designer used also a real-time workshop to embed their new strategy in rapid prototyping. So at the end of this step, we've got information about microcontroller resources consumption. And we know also that models can be coded with real-time workshop. So for the software team, the output of the design phase is what we were expected for many years. I mean, we've got models that are executable, and we also have expected behavior description provided by the simulation. As a complement, we also have information on microcontroller consumption, resources consumption. Okay, so at this point, we can start with a real implementation process. The implementation process is divided in 4 steps. The first one is the one we call architecture. We've got to make some reworks on the design models for many reasons. We've got to introduce specific software requirements in the models. We've got to introduce our software optimized libraries in the model. What else? We've got to introduce also basic software APIs in the models, and so on. So, previously to this first phase, to this first step, one software control is done on the model to be sure that the implementation step could be launched in a good way. And for this, we make complexity analysis. So part of the analysis is done by tools to count blocks, IOs, and so on, and also manual human analysis to check for function call organization mostly. A very important thing is to check for model coverage of the simulation. We'll see later that it's really important for us. And we also use a homemade model checker, which has quite the same features than model advisor, but with some additional features that we need. And due to the fact that we make some reworks on the model, we've got a first non-regression test at the end of this step to be sure that model still have the same behavior that the initial one. Okay. The next step is a real software implementation step. At this step, we introduce all software features like data typing, memory mapping. We manage data type propagation, saturation, overflows, and so on. And at this step, we also introduce AUTOSAR features in the model. All of this activity are done with Simulink and real-time embedded coder. For AUTOSAR workflow, when the AUTOSAR target is selected for a real-time workshop embedded coder, we've got an interface to describe all the AUTOSAR features for input, outputs, and runables. Okay. At the end of this definition, we run a second time our model checker, but we use much more restrictive rules to check implementation and software rules. I mean, this checker allows us to check for saturation and so on. It's from my point of view, quite impossible to check a model and model configuration by a human way. There are too many checks to do, too many information to be validated. So once the model is checked and all the rules are validated or justified if they are not respected, we generate the embedded code as well as the S function by using embedded coder. And the software model is then and the software code is tested using SCL process. Okay. As a complement, we run QSE and polyspace analysis, mostly to check for overflow management and runtime errors. The last step is software delivery, and still with embedded coder, we are able to deliver a consistent package, including the C code, the A2L files, and also the ARXML files. We also reuse one more time the simulation to extract, integrate information to build our integration test plans. We use the simulation one more time to describe expected value for a given input set. So, one also very important point is that we wanted to deploy this new coding processes, but we wanted to keep all the support processes that we had for project management, for requirement management, issue management, configuration management. It was very important for us to keep all those tools and processes as we had before. And so we just started with the models and the simulation to generate the code and to make verification using MIL, to make verification using SIL, and to reuse one more time simulation to build our integration test plans. So for us, automatic generation of code must be a logical extension of model-based. We reuse all the outputs of the functional design phase, and we only had to adapt our test strategy to be sure that there was no regression on the models and on the generated C code. As a conclusion, I will give you some key data. So we have developed something about 20 applicative software components. The integrator project has integrated those 20 software components, but also 20 other ones coming from other suppliers. We also introduced lean basic software as an AUTOSAR basic software. We used commercial RTE tools and authoring tools to integrate the components. And we had to develop many tools to integrate, to interface all software with RTE to be able to read information on RTE or to write information on RTE on our existing software. To be able to start with those new processes, we had to ask for requests for external support, and at first we used Valeo Center of Electronics Excellence, which is involved for many years in AUTOSAR consortium, and delivered us trainings and description of AUTOSAR principle and so on, and many support to be able to handle those new components. And we also had a very good support of the MathWorks to be able to use embedded coder in a AUTOSAR context. So the benefit that we had with this new process was first, it's a time-efficient solution to develop. I won't give you any number because many things came at the same time during this deployment. We had to increase simulation coverage. We had to fit with some missing functionalities and so on. So I won't give you the result just right now. We consider that the benefit is also a quality efficiency because of the reuse of simulation during all the development cycles. We also used additional tools and mostly VNV to check for simulation coverage, which is very important in our process. And what we consider also very important is to be able to switch to different AUTOSAR release using the real-time workshop embedded coder. For us, it's a solution to manage the different AUTOSAR release. And last, the very important point is to have a consistent package for our deliveries. And what was also very interesting is that Simulink uses a very well-known script language that offers the opportunity to make some customization and automatization in our process. So we had to we made those development with the 2008B release, and there was some missing functionality for AUTOSAR. For instance, the AUTOSAR runables at the beginning must be at the top level of the models, and for us it was quite a problem because there were no constraints for designer, and we had to ask to MathWorks to help us with a pilot support package to be able to manage our existing models and work around these constraints. Second one was inter-runnable variable produced by multiple runables. The merge function was not available, and we also had to fix this point with a pilot support package. One feature of embedded coder in AUTOSAR with the AUTOSAR target is that he is able to deduce AUTOSAR runables from function call description in the model. So I would say for nominal models, it's a very, very efficient way because we have no definition to do. For complex models, it has been one constraint, and we had to make some rework on one particular function. We had to make one big rework to remap, in fact, the subsystems according to function calls. Last point is that we had no processor in the loop solution with our microcontroller with embedded coder solution. And so to conclude, I will insist on what I consider to be the major point to be able to start with the automatic generation of code. First point is for sure to have some standard block libraries and to share those libraries between designers and software teams. It's something very important. Second point is to have a model checker, because I consider it's not possible to have an exhaustive check, a human exhaustive check of all the configuration of all the blocks and so on. And the last point is that we also need simulation with full coverage of models. It's very important to be sure that after implementation step, the behavior is still the same. So for this, we use coverage measurement tools, and we have got processes to increase the coverage when it's not full. And some software tests cannot be done on models, and so we've got also to make specific tests on generated code. And for this step, we use mostly polyspace, which covers all the points that are not covered in the model. That's all for me. Thank you very much.